Hello and welcome to the Battery Innovation Podcast, the podcast about today's innovation for the technology of tomorrow with scientific reputation. My name is Simon Voss and I'm the chief and founder of Battery. And today I'm delighted to welcome Professor Dr. Bernd Friedrich to the podcast. In collaboration with the Aluminium Innovation Cluster of RWTH Aachen, Professor Friedrich and his team conducted a study for the European Aluminium Association as well as the International Aluminum Institute about the current status, potential and challenges that purification of recycled aluminum raises, as well as shining light on potential solutions that are on the horizon. I'm looking very much forward to the conversation. All right, Professor Friedrich, thank you very much for inviting me for this conversation about aluminum and your work regarding especially recycling, but we'll come to that topic in a bit. Before, I would like to ask you about IME and your path, your academic path in the field of metallurgy and beyond. So maybe you can just introduce us to your work, your research, and what your team currently does.
Okay, the IME here in Aachen is mainly dealing with process metallurgy and metal recycling. Metal recycling at the end of the recycling path. So when people have sorted scrap and then we receive that and we try to produce a new alloy from that, a recycling alloy, which can be used from everybody in the world here again in our consumer products. This is a part of the University of Aachen. And 10 years ago, we have created an innovation center. It's AMAP, it's Advanced Metals and Processes, which I also co-founded. And there we have a very close collaboration with industry.
Okay, so to sort that out really quick. So you have the research chair of IME, and then RWTH is a big university, as many of us probably know, which also is very focused on supporting industry or helping innovation pathways towards industrial adoption.
That's right.
And what you just mentioned, AMAP, is a cluster as such, where research and industry comes together, correct?
That's right. So we define projects together. And interested parties, university, institutes and industry partners form this project, and then they join, let's say, even our office together, a meeting once a week.
Oh, wow.
And discussing a specific topic. And university, of course, has the advantage of some PhD thesis, doctor thesis. And the university also then brings in all the infrastructure we have. And industry brings in their know-how and their lab and the industrial scale tests.
Okay. So how much industry partners are involved and how much research is involved? Can you give us just an idea?
It's almost the same number, roughly 10 to 12 institutes and the same number of industry. OEMs, like car manufacturers, on the end, you can say, but at the beginning, these are companies who are producing aluminium, recycle aluminium, and forming new products from that.
Okay, so you just mentioned OEMs, so it's really across the whole value chain, if I understand you correct.
Yeah, that's right. Yeah.
So from the mineral company who is digging in
one
the ground.
One of the OEMs is Ford, for example, inside, or Toyota. And on the other hand, we have the primary producers like in Germany, it is TriMet, which is one of the forerunners. So it brings together also for the industry, yes, customers and producers, and on the other hand, the university researchers.
Okay, so before we go further in the direction of shining light on what recycling currently the status is and the current challenges and potential, what are, besides recycling and upcycling, we will come to that in a second, what are the big projects that you're working on at the moment in your field?
So,
if you can give us
it's not only aluminium.
Big map.
So we are not an aluminium research institute. In the moment, the biggest area is battery recycling. Includes not only the battery itself, but also the housing. There we have the aluminium again. And this aluminium should be made in future from recycled material, because that is a little bit a demand of the OEMs to have to increase the recycling content in all products of the car.
Yeah.
The second one is electronic scrap.
Okay.
Which is everything like from smartphone to laptops to mobile devices.
So including the battery, but probably also the electronics. I think
The whole
on the
electronic
PCBs, so the printed circuit
PCBs,
boards.
printed circuit boards.
There's a lot of
computer
gold
chips,
and precious metals on there, correct?
That's right, a lot of precious metals inside. So we are dealing more or less with more than half of the periodic system of the metal. So there are more than 40 elements in a smartphone, metals.
Wow.
So, and only a few of them are recycled, and most of them are lost during the recycling process because
Also nowadays.
Nowadays, yes.
Wow, it's hard to imagine, or
Because of the small content. Sometimes you need a capacitor, for example, for the 5G network. There are only a few milligrams of tantalum, for example, inside. And if you recycle a smartphone, it's very difficult to recover this small amount. But it's very important, and we are depending in Europe on all these metals. And in the last 50 years, we more or less closed all our mines.
the mines in Europe, you mean?
The mines in Europe. So we are dependent on imports.
Yes.
And so recycling more and more comes in the light. But on the other hand, our institute, of course, is also working with the primary producers, aluminium from raw material, nickel from raw material, and so on.
Yeah. So the application fields were batteries, power electronics, or electronics in general.
A lot of industrial wastes.
Industrial waste. So what is that?
Because they are moving in this closed loop concept. So we don't want to make landfilling materials anymore. That means it dust, sludges, slags, and something like that. But it's also, like, if you look in future, when we produce hydrogen, we need hydrogen electrolyzers, fuel cells. So they are coming also to us now. At the very early beginning of a...
They need platinum, correct?
They need platinum, that's right. The whole CO2 minimizing concept is touching everywhere.
Okay.
Green Deal, you can say. So how to produce metals or products with the lowest CO2 footprint. And every time we are involved. So there's not one European project, I would say, which tried to produce or develop a new recycled alloy where the metallurgists are not involved. Life cycle analyses have to be done. The footprint, climate control, and these things.
Yeah, I heard once when I was in my studies, a couple of years ago already, but I was talking to a metallurgist, and he said, like, because I'm a mechanical engineer and by heart, and then he came to me and said, like, hey, did you know that every innovation that is out there was due to a change in material innovation? Because due to the new material, a new functionality was achievable, right? Let's take steel or other composite fiber or whatever it is, which opened up new possibilities. And it was always the material that was first, and then the creativity of engineers that then came after. I find that very inspiring.
It sounds good, but also I think more and more the demand comes from the product side. So for example, we consumers, we want a laptop with more storage capacity and higher speed and something like that. So the demand is now to us, please purify the metals better. So please remove all these impurities to a lower degree. And so therefore, that is also a pressure now. It's not only that we are able now to make purer metals, and then the application follows, more and more also the demand comes from outside to us.
Okay. So then the question is for me now, you brought us a little present. This is not aluminum, what is it?
Yeah, it is aluminium inside, but it's not aluminium metal. So what we see here is a nice piece of bauxite. This is the worldwide only raw material where we produce aluminium from, in more or less in the tropical areas of this globe. It contains between 25 and 40% aluminium oxide, but the color here, the red color, comes from the iron oxide, which is more or less parallel in this mineral. And aluminium is a very ignoble metal, so it oxidizes easier than iron. So there's no aluminium as a metal in our nature. It's all oxidized.
Yeah, so all Al2O3?
Al2O3 or more complicated formulas.
Okay.
Yeah, and
this is what you learn in
so all the aluminium in the world, which has been created by our early beginning of our planet and maybe even the whole world, is oxidized.
Okay.
Yeah.
So there is no pure aluminum available in nature?
No, not available. So there was a lot of energy released when the aluminium has been oxidized millions of years before.
Yeah.
And we need to put all this energy back to the system to recover the aluminium as a metal back. And this energy, of course,
which means basically that you remove the oxygen from the aluminum.
Firstly, we remove the impurities from the aluminium oxide.
So first step, you come from the bauxite to the aluminum oxide?
Correct. A white powder.
Okay.
Yes. That already costs mining energy, milling energy, chemical energy.
And has byproducts, correct?
And has a lot of byproducts. A so-called red mud is created. All this reddish colored iron oxide is remaining on a filter and is then landfilled. That has a large impact on safety, on environmental topics,
concerns,
and all these things. Concerns, yes. Even accidents sometimes.
Okay. So and is this also an area of research where one tries to reduce the percentage of the mud that is created, or use the mud even as for construction or something else, that it doesn't have to go to landfill?
Yeah, it is not a research in my institute.
Okay.
But worldwide, of course, minimizing energy needs, chemical needs and all that is certainly always a topic. But there are thermochemical limits. You need to put at least the theoretical energy to the system.
Yeah.
In reality, is more than double, because you never reach the theoretical values. And so we put so much energy into the aluminium that afterwards, when you have the metal in hands, it is not only a metal, it is really an energy storage. So all the energy is stored in the aluminium.
You mean the next step, right? So you have the aluminum oxide.
Yes.
And then you process it further to reach pure aluminum without the oxygen.
We need to crack, you can say, the aluminium oxide into
the
aluminium
oxide
and oxygen.
layer open, right?
In aluminium and oxygen. Then we have the metal, and it sounds good that we have oxygen. But unfortunately, this oxygen is burned off with carbon in the classical electrolysis, because we need so-called anodes there, and they burn off, and so we have CO2.
Yeah, which raises the fact that it's so important to keep already pure aluminum pure, or recycle it, to not have this huge energy effort again, and the environmental impact to take out new aluminum. I mean, that is inevitable probably, because our economy demands quite a bit of aluminum as far as I understood. But then through recycling methods to keep the already available aluminum in the cycle.
Correct.
Right?
Yeah. But you can say about 1/10 of energy is needed in recycling than primary from the ore, and only much less than 1/10 of waste is generated when you recycle. So it's not a zero waste process, unfortunately. It is impossible. Zero waste sounds nice, but it's theoretical only. So very limited amount of energy and landfilling effects.
Okay. So you did a study, right, on purification challenges and potentials out there, the different pathways that are in the technological realm at the moment, that are going to or actually researched and innovated further. I would like to touch on this and give an overview of what the current pathways are, which are promising, where are challenges, etc. So can you give us a little overview? You have brought a slide. If we can mention a couple of different pathways.
Yeah.
There are too many that I can oversee them at the moment,
Yeah,
but you
yeah.
help us
It is,
to
of course,
dissect
it's
through
of
them.
course complicated.
Yes.
So we touched the needs of recycling. So when you go on a scrap yard, yeah, where the recycled aluminium is collected, you will find 20, 50 different product types.
Okay.
Yeah. It starts with very simple and clean scrap and it ends with very complex mixed scrap with organics and other metals and so on.
Organics, everything that contains carbon,
Even containing
polymers,
carbon, polymers, correct, a lot of plastics inside. But also, let's say, if you look to a car, after its use, it goes to a so-called shredder. So everything is crushed down, and then through different separation and sorting techniques, the light metal aluminium is separated. Separated in a certain fraction, but that is also not 100%. So if you have a cable together with the aluminium, also the cable is scrap, and you have some parts of copper in the aluminium and a little bit of iron and everything. If you have a solar collector there, there's a little bit of silicon there.
Okay.
So the shredded and sorted material is never clean, and day by day the composition is a little bit different.
So this is also how it's done in practice, right? You have all the trash, like the electronic waste, like smartphones or now coming up batteries also from electric vehicles. And this is all dumped in a shredder and then grind it apart so that you have little flakes of different sort of material.
But not everything together. So maybe you have all smartphones together, or all PC printed circuit boards together, or car separated. But each of these, let's say, beneficiation techniques create a certain concentrate of recycled aluminium.
Yeah.
And each of these, you can say, boxes then contain also a different mix of impurities. Sometimes very difficult to forecast. If it is a production scrap, much easier. If it is a consumer scrap, very difficult what is on the truck coming on.
Yeah.
So we have a multi-metal system, mainly aluminium, but a lot of other impurities. And we will find that more and more in future because Europe has decided to reduce the amount of primary aluminium and to increase the amount of recycled material.
But that demands a circular economy.
That is circular economy. That is what we want.
Yeah.
It's a circular thinking. Circular thinking is not only recycling. It starts very early, yes, in reuse, in remanufacture. Also rethinking of the whole concept in small startup which separates by different topics and bring the aluminium back in with new business models. It's all circular economy.
Okay.
We are, you can say, more or less at the very end. If nothing helps in reuse and remanufacture, then we have to recycle.
Okay.
So recycling is always positive because people think, and it's correct, that is a green process. So we have to deal with all these impurities, and the European Aluminium Association in Brussels and the International Aluminium Institute in London asked us to compile the existing know-how of removing these different impurities from a recycled aluminium.
Okay.
Because people are melting it down, and then you have a melt. It looks homogeneous, it looks like aluminium, but it contains a lot of...
From a metallurgical standpoint, it's not that what you need in order to build performance.
You cannot cast it into a new product and then think you have made a good product from it.
Yeah, because the material properties, the ductility or other tensile strength.
Very simple development what we have, which a normal consumer don't feel, but it is enormous important. The change from combustion engines to electrical cars is now going on. So the combustion engines, they are based on a cast aluminium block.
Okay.
Yeah, where the fuel is burned inside, and
Yes.
it's a very high alloy, a lot of silicon in, a lot of copper in, a lot of iron in this aluminum alloy.
What properties does it provide?
Castability.
So from a
If
manufacturing
if
standpoint.
you look to such a block,
Yeah.
you will see very fine filigrane channels, where cooling water is passing through, and ribs where the cooling air is passing through.
So convection
So
is
very
possible.
complicated casting structure. So we need a very good castability alloy.
Okay.
And of course, corrosion stability. So a lot of properties, but castability is the most important.
Okay.
Highly alloyed.
All right.
But in future, if we have the change to electric cars, we don't need these blocks. And what will happen in the next 10, 15 years, they will all return for recycling. But nobody needs this alloy anymore. Or at least
We need to
much
get the
less.
silicon out
We
and
need
all
to
the
get
other
at least
impurities now.
correct.
Yeah.
Now you can say, okay, what is about electric cars?
Yes.
They also need aluminium. Especially they need a large box for the battery.
Yeah.
And this
Cell housing,
box now,
prismatic
you can say it's very nice because it contains aluminium again. But the demand or the property demand is different, because now we need ductility. Yeah? If you have a crash, something like that, this box need to be able to have some torsion stability and something like that, not directly crack off and the battery goes up in fire.
Yes.
So that means we have to reduce the alloying, you can see spice metals in the to a certain degree. We don't need to
It's the
produce
salt in the soup.
super pure aluminium, but we need to reduce these elements. Yeah,
Okay.
we call that upcycling. So we increase the chance for reuse.
Okay.
Yeah, and
So does it
that's
mean-
currently going on.
Yeah. Does that mean that you take out all impurities first, or you take only out those impurities that you don't want to have in there anymore?
In this specific case, we only take out the minimum amount necessary.
Yeah.
That otherwise it would take too much energy and time to go down and re-alloy. Yeah?
Yeah, because as you also explained me before our discussion, off mic, so to speak, that not every path can extract all elements, right?
Correct.
So maybe we can touch on this really quick.
You
What
see here,
paths are available?
You see in the black bold text, these are the different technologies. Yeah, what you see here is the different technologies in place or under development.
Okay.
There are a few which are able to remove a handful of elements, as you see here. Some only one or two of these elements.
Yeah, like zinc,
as you see,
magnesium.
vacuum distillation is possible to remove zinc and magnesium because they have a high vapor pressure. So that is not a very big problem. Boron treatment is also in place, but it's only possible to remove titanium, for example.
So you bind these elements to boron then, or how,
Correct.
So is that scrap then?
That's
The boron compound?
the boron.
Is that scrap then afterwards?
No, the boron is added. The titanium combines with the boron,
Yeah.
forming a boride.
Okay.
And this boride has then, this is a solid particle,
Yes.
inside a liquid aluminium. And then we have to remove this.
So under high temperature, right?
It's a high
liquid
it's
aluminum.
800 degrees, something like that. So we have to filter it, or we have to bubble gas through it to take the particles out. So that is possible. But you see, you don't find zinc and magnesium there. Yeah.
But that, maybe if I to get this right, so you have afterwards boron and titanium as a
Together as a compound, as an
Yes.
as a non-metallic inclusion, you can say.
Can this be used in other applications afterwards?
Not really.
So this is scrap. This is landfill.
It's a very small amount,
Okay.
but typically you cannot use that.
Yeah, I think what we have to get into perspective here are the orders of magnitude, right? We are talking about hundreds of tons of aluminum, and then just small amounts.
Sometimes 0.1%, 0.5%.
Yes, so it's like grams amount of these
Correct.
specific impurities that we take
Sometimes,
out there.
if you talk on tons, of course, it's maybe kilograms.
Yes, of course.
Yeah, but you are right. It's a very diluted level, but they influence
The mechanical and electrical and
harmful
chemical properties.
Correct.
Okay,
So what you
gotcha.
see here, there are different technologies which we have compiled in this study with what is the state of art and what is the chance for upscaling.
Yes.
Some are already in place. There is a technology readiness level, TRL, defined. If it's very high, let's say 8 of 10 or 9 of 10, then you are already in production.
Yeah, so maybe to give this a little bit elaboration, the technology readiness level defines, as the name says, the readiness level on a scale from 0 to 9.
Correct.
Right? 9 meaning industrial adoption, full-scale production, and 0, 1, 2, 3, like early research, and then 3 to 4,
That's
like
right.
pilot line, and then prototyping, and then small series, all the way up to 9. Then.
Yeah. And all of them have different TRL levels, so reach technology levels. And what you see here, if you have a very complex scrap mix with all of these elements, you cannot use only one technology.
So maybe to give an overview first off before we dive into further pathways, which of these are low TRL and which are high TRL?
So upper left, so boron treatment, gas purging, salt fluxing is high. This is in industrial already integrated.
Okay.
But for example, you cannot see nickel there, you cannot see copper there, which makes it complicated. On the right side, intermetallics, vacuum distillation, also selective oxidation, they have quite low, you can say 3 to 4 or something like that. And on the bottom line, these are
the 3-layer electrolyzers.
Very promising technologies, because you see 3-layer electrolyzers for all impurities.
Yes.
It sounds very good. Yeah, so this is the wonder technique, you can say. It worked with different electrolyzers, let's say systems, but not fully developed. It's still in the research state. You say
what number would you give it?
2 to 3,
okay.
Something like that. And of course, it will again involve energy if we put into it, because we will dissolve the whole aluminium and we will deposit it again. So that you can say we make more or less half of the primary route again.
Okay, so you have to liquefy it for that?
You can say, to liquid, you can, but if you go to an electrolysis, you will transform an atom into an ion. Yeah, so it's dissolved in an electrolyte.
Okay. That's...
And then it is deposited on the other side again. And by this, you can control. We call this the potential of the process, that all noble metals will not dissolve, and all more ignoble metals will not deposit.
Yes.
That means we allow only aluminium to go through.
Yeah, so the electronegativity is the
aluminium is very ignoble.
Driving parameter there.
So most of the impurities are more noble, which we bring in through electronic scrap and iron, chrome, nickel, copper, platinum, gold. Everything is more noble.
Yes.
And therefore, processes where we try to oxidize will never work. Or chlorine, we use with chlorine or something like that. So electrolysis is good, but it's still under development. And
energy
afterwards,
intensive.
again, what to do with the remaining alloy, where all the noble metals are enriched, and what to do with the electrolyte, where all the ignoble metals are enriched.
Yes.
So these are the questions not solved up to now.
To give an understanding of the weight percentages again, so we have then the aluminum that is ready for recycling, or that is...
It is super quality.
Yes, but what percentage do we have this slag in the end?
The electrolyte, you mean?
Yes.
That is depending on the impurity level, of course.
Okay, so that is...
but
can you give a range?
Between, I would say 10%, 5 to 10% of the input scrap may stay as a remaining alloy with high copper content, high nickel content, and all these elements are enriched. What to do with that? Of course, you have maybe 90%, 95% of aluminium purified, but it's cost, right?
Yes.
And the electrolytes that can normally use for many weeks. But if the level goes up too high, then we have to remove it.
Short question. If you say cost in terms of economic cost, in terms of time, what are the limiting factors there to scale this?
So electrolysis generally is a slow process.
Okay.
So
you need a high bandwidth in order to have a high output.
We call them the reactors. We call them electrolysis cells, right? And each of these cells produces maybe a ton per day, not more. Sounds much, but it's not really much, because a recycling plant today needs 50,000, 100,000 tons of aluminium produced per year. And you can imagine there are a lot of cells involved. And each of these cells needs electrical supply, needs maintenance and all that. So it's quite a costly process.
Okay. So there's one last option, and that's fractional crystallization.
Correct. Yeah, this is a process which is industrially used for super high purity products. So for example, for silicon, for solar cells, for germanium and tellurium, for electronic devices, even arsenic, which is normally a poisonous metal.
Yeah.
In a very small amount, it is produced by this technique to produce gallium arsenide chips, computer chips. So you need, because it's electronics, you need purities of 79, that means 99 point, and then 99999, yes, percent. And germanium, for example, for space application, solar cells, they need 13.9 purity. So that is in place for small amounts, not for the large 100,000 tons.
Yes.
So therefore, and we don't need the 39s. We come maybe with 1 9 or 2 9, so 99.5.
Yes.
Yeah, and we want to reach only 395 or 49. That's for us okay. So
okay.
we know how it works. It is a principle where we controlled, crystallize or solidify the aluminium, and the impurities stay in the liquid phase, and a block is created very slowly, yeah, very controlled, where all the impurities are pushed away from the front, and afterwards you have a very nicely purified block.
Of aluminum?
And, but again, like electrolysis, all the impurities stay at the end in maybe again in 10%. At the top or on the left side, it depends if you work horizontal or vertical, doesn't matter.
Okay.
Yeah, but the same with the electrolyzers. Yes. What to do with the aluminium, which at the end, which collects all the impurities. So again here, it's a question of scalability.
Yes.
So therefore, I would say TRL level for these electronic metals is 9.
Yes,
yes?
But
even aluminium is produced like that in super small amounts for electronic devices. 9.
Yeah. So the question then is, on an industrial scale, what is the TRL there?
Yes, and that is 0 in the moment. Yeah? Okay. So nobody refines aluminium in the moment by fractional crystallization.
If you would have to choose to bet on one path, or maybe you tell me now that that's not possible, but what innovation pathway do you foresee for the aluminum industry to be scaled and industrialized to enable, not perfect, as I learned up to now, recyclability, but as good as possible recyclability in terms of cost, scalability, environmental implications, etc.
Yeah. So first of all these process steps are not optimized completely.
Okay.
So there's a lot of research going on, yeah, to use boron treatment, yeah, maybe also for other elements, which come more and more in the scrap flow, and also to minimize the boron content and to minimize the production time, energy use, and all that. So firstly, I think we all have to optimize these processes. Vacuum distillation is not really in place, but for zinc and magnesium, it has a high potential. It is more or less researched to a wide range, And the big advantage is, if you look on boron treatment, on salt fluxing, on selective oxidation and so on intermetallic formation, they all create a new compound. They all create a new product where you have to find an application for that. Vacuum distillation, on the other side, it produces the metal again. So you recover zinc as zinc and magnesium as magnesium, because it's like an alcohol distillation. Yeah,
with metals. That sounds really interesting.
Correct.
And it sounds like very high temperature.
No, well, not very high temperature, maybe low pressure.
Okay.
Yeah, so it is as the main word vacuum means.
Yes.
It is fully okay if you exceed the aluminium melting point of 700 degrees
Celsius.
But then you reduce the pressure, and the more volatile elements like zinc and magnesium leave by bubbling, you can say, the melt.
Wow. Okay.
And you condense it as metal.
Yeah.
There's no oxygen in the system.
So, but not applicable for aluminum. That's as you mentioned, or
yes, it is applicable. So if you have aluminium with a lot of zinc and magnesium,
yes,
but aluminium is not evaporating.
Yeah, sorry. My question is, so that is only available for this particular alloy with zinc and magnesium.
Yes.
For an industrial route, but if you need to have a process which covers all the other impurities. Talking about the battery industry, you just mentioned nickel, right?
Yes,
So there are coming battery cells with a lot of nickel and manganese on the market. On the other side of the electrode, or the other electrode is copper. So very likely copper will be around as well. Cobalt is another element. Just talking about my field, right? So which technology do you use for that? This messy, complicated alloy.
The biggest chance has electrolysis. So we are talking here about very noble impurities. Copper, nickel, lead, of course gold, but you have to look about the scrap flow. The chance that gold comes in contact with aluminium is very low. Yeah, so if you look to electronic scrap, where is the aluminium there? It's the cooler for the computer chip.
Yeah, and that brings me to another question, because recycling is one, but before you start the recycling process, you can remove parts, right? You can take it apart. And I would like to ask to give an overview what role sorting takes and what role recycling takes, and how those two can be in perfect balance to find a Pareto optimal solution then.
Yeah, I made a very nice drawing about that. Maybe I can send it to you.
Yeah, we can flip it in here.
It is very simple. We metallurgists can take the scrap as it is. But then later on, we have a lot of work to do for removing all the unwanted metals and impurities we have. On the other hand, the mechanical guys, I would say, call them, not chemical, not metallurgical guys, they can do a perfect job by manual dismantling, using pincettes, and separating piece by piece and put it in a box. Then we metallurgists have a very easy job. Because all the tantalum capacitors are there.
So who's doing the work now?
And if you take each piece of aluminium and make an X-ray analysis on that and say, this contains manganese, go in this box, that would be very nice and perfect for us. But now you see, it's a little bit funny for that, because that can never be industrialized. So now you go on industrialization. Industrialization means you have crushers, but before the crusher, you have a separation in the scrapyard by, let's say, by people who have a lot of know-how. When a truck comes in and say, these are maybe pieces from car wheels. Put that in this box and don't mix it with the other ones. So the first job is just separating the scrap in part. If it's very complex structures now, you have to shredder to minimize the size. And then this shredded material goes through, I would say, a multi-step process, which uses sensors, online electronic sensors with artificial intelligence computers behind, and they can distinguish by magnetic properties, by color, by density, even by shape, yeah, by eddy current systems. They can then split on completely running continuous lines into different boxes, but they are never 100%.
Yes.
Yeah.
Yeah.
So simple as your battery, for example. If you shred that, you have a copper foil there and you have an aluminium foil there.
Yeah.
But they end up as a mixed scrap.
Yeah, and on that foil, especially on the aluminum foil, we
Another
have a lot of
another
precious
impurity
metal.
is on that. But
Yes.
only copper and aluminium cannot be separated by just shredding, because if you have foils, you know that from your kitchen, aluminium foil is very, very soft. Yeah, if you shred that together with copper foil, you can never separate them again.
Like mechanical intercalation.
Yeah. So now you have a copper aluminium. So what do you want to do that? Go to give that into copper industry, then you lose the aluminium forever. Give that in the aluminium industry, they don't want the copper.
Sounds like they have to work together.
They have to work together, but also we as a researcher, we have to find better solutions. So therefore, I would say the best economical sorting technique helps to improve the whole recycling chain and minimize the energy input we as metallurgists have, and also minimize the waste we produce.
And as a mechanical engineer who also has a focus on the development of products, let's say, on batteries and especially in battery production, you can also go one step back even and think about how you can ease the dismantling of the whole system and make it ready for reusability, remanufacturing, or then when you opt for the recycling pathway, first go through a sorting process where you can sort it really well already, right? Where you can use visual inspection systems, which then can detect, okay, this is an aluminum part, this unwind, for example, battery cells, you just mentioned them, right?
Yeah.
So take out the jelly roll, unwind, and then first separate aluminum and copper. Things like that.
I think a lot of things are possible.
So from a design perspective,
the only thing is what is scalable,
Mm-hmm.
what is the price for that, how sensitive it is. So we call this also adapted technology. So what runs here in Germany may not run in developing countries. And a lot of scrap is generated in developing countries, so Central Africa, in Middle America, or wherever. So you
shipped there, right? I think that's also...
Now the question is, should they ship the mixed scrap to us? Then they will get paid very low. Or do they have the chance to separate already in these countries?
To upcycle there.
Upcycle there and so on. There are different techniques and optimizing levels, you could say, in place. But you're right, the mechanical separation, sorting, concentrating is very important for future, let's say, enabling circular economy for metals.
Okay, so to sum this up, to provide an overview, we start with this block of impurity, so to speak, which is a mixture of different oxides. We take a lot of energy in order to generate, synthesize, you call it?
Yes.
To synthesize aluminum. And then the aluminum is alloyed to yield certain mechanical properties, which are case specific. So we have, for different applications, different alloys.
Yes.
And always have to make sure to get back to a relatively pure state to be able to reuse the aluminum for another application in its second life, or third or fourth life, right? The pathways there are all yet under research and development, and there are, besides all the recycling methods, also the options of doing a proper design and sorting to lower the cost of the whole, of closing the loop, so to speak. Yeah. Correct?
Correct. And that is, if we go back to our cluster, that is the big advantage, that people from sorting, people from concentrate, OEMs, producers, they are all there. Yes. Yeah? And you all get the information of their problems.
That's cool.
And they understand more let's say, are the challenges of a metallurgist. So they are sitting together, and discussing and optimizing the pathway. So we have projects, for example, on upcycling, on vacuum distillation, on boron treatment improvement. We have projects on electrolysis and so on.
Okay. So you would say that the collaboration in that space is working well and that Europe stands together on this matter because everyone understands that closing the loop is so vital for our economy?
Sounds good. Europe stands together in this specific small case, where I would say companies and institutes which have collaborated in the past since many decades, they know each other and they trust each other. They form this cluster. In Europe, we have so many countries and they start immediately from the beginning as competitors. They don't trust. They don't tell. And that makes it very difficult. So everybody starts the development on these fields. So we have redundancy everywhere, everybody doing the same, not aligned.
But I think that's why we're doing this recording right now, to get out the information. What is your current status on the technological development here? Who could be a partner potentially to push this or that or this technology further? And I would like to see a sustainable, energy-efficient pathway on providing a lot of more aluminum to our industry, preferably recycled aluminum.
Must be recycled material, otherwise we will not survive in Europe. And we have only to buy the material from outside, and we are extremely dependent. If they don't supply, we cannot produce. We lose the industry, maybe even from the top down or from bottom up. It doesn't matter. We lose our industry level, which is the strength, especially here in our highly industrial countries.
So maybe to conclude with this outlook, what is the percentage of recycled aluminum in our industry right now? And what is the percentage that we still have to get from outside?
Germany is a forerunner. We are roughly 50%.
Of recycled aluminum?
Yes. What we treat here, you can say, is recycled aluminium. But we are best in class, you can say.
Okay.
US is much smaller, and countries in South America, for example, and also in China are even much smaller.
Okay.
So, in case you are dependent from raw material supply and you don't have mines anymore, and you don't have the energy cheap, like
that's
in
a
Germany,
vital point, right?
Yes. So then you lose these primary techniques. And the only chance in energy is, let's say, green electrical energy, like water based energy, solar, wind. The French people think nuclear is an alternative, but I don't think so.
If you crunch the numbers, it's very likely it's solar and wind.
Correct. So as we mentioned, it is a big question of energy. And as recycling has only, I mentioned that, 10% and less energy, it is the solution for our country here.
Okay.
Recycling.
We'll do so. So closing the loop and then seeing that we increase the recycled content even more beyond 50%.
Never have 100% loop. That's impossible.
Yes,
it's
of course.
only possible if you don't have an increasing market. So we have a 98% closed loop in our lead from the lead battery, lead acid batteries, because there is not an increase anymore in the market. And we have to pay a deposit, and then later on we bring the battery back.
Yes.
So this is a super system, but as there's no growth, we can rely on recycled lead. But this is the only metal where we have more or less a saturated
functional circular economy.
Saturated system. Yes.
Okay, so let's work together and towards with your consortium to also allow this for the aluminum industry then.
Yeah, and refining is, I think, the key. If we are not successful here, we will not be successful at all.
Okay, but let's try to be successful.
Yeah.
Thank you, Professor Friedrich.
It was a pleasure.
too.